framework like integrative weather-informed routing and energy optimization for sustainability maritime transportation.
Okay, so I think it's a serious problem. So now let's start meeting.
Based on the PDF research from our topic, which is integrating weather-informed routing and energy optimization for sustainable maritime transportation. For this research problem is about reducing greenhouse gas GHG emission and increasing the energy efficiency for maritime transport are two of the most urgent concerns facing international transport today. Raise the sustainability of marine logistics. So the first methodology is the authors developed a database model to estimate ship resistance from wind, waves, and sea currents. This is combined with a 3D dynamic programming algorithm to plan optimal ship routes. They also use a mixed integer nonlinear programming approach, which includes factors like refueling, time limits, and port assignments. So the main findings of this study is found that the proposed method reduces fuel use, travel distance, and journey time. Using one ship for multiple destinations is often more efficient. Though in some cases, multiple ships may be better. Overall, the approach improves efficiency while cutting emission. This for the interpretation, this reflects a shift towards data-driven, flexible strategy in shipping. The study shows that sustainability and operational efficiency can go hand in hand, helping companies meet climate goals and reduce costs. In conclusion, the study offers a practical solution for greener maritime transport. With rising regulations and unpredictable conditions, weather-informed routing will be essential for the industry future. So I have some questions here. The analysis of various cargo delivery scenarios indicates that deploying a single ship for a limited number of destinations is more efficient compared to utilizing multiple ships. So what's your opinion?
I agree with the statement. According to MEAL.2022, seafares is heavily disrupted by port congestion, labor strikes, extreme weather, container shortages, and customs delays, with U.S. shipping reporting that 43% of 5,410 ship arrivals were delayed by at least 1 day due to limited cargo space and reliance on multiple ships. Besides, according to D'Agostini and other 2024, to stay efficient during COVID-19, shipping lines like JIM and MAX use fewer smaller ships, made fewer port stops, and extended port stays. This streamlining approach earned them efficiency scores such as 1 and 0.95 in data environment analysis, proving that focusing one ship on limited routes boosts fleet use and cuts access capacity. In addition, according to Christensen 2019, using fewer and larger ships on optimized routes boosts fuel efficiency per container mile and cuts overall costs, while hub and feeder systems offer flexibility, they raise handling costs. So network pricing favors fuller ships and fewer ports costs for better efficiency.
So this study employs a semi-detached environment model to precisely estimate ship resistance to waves and other environmental factors. So what's your opinion?
I disagree with the statement. First, according to ATL.2022, for example, additional resistance is strongly influenced by stem profile and bow shape. Model tests found that a vertical stem without a bulb reduces resistance more than a traditional bulbous bow across all wavelengths, indicating that semi-empirical models may misestimate resistance by overlooking these geometric details. Next, according to Peterson 2020, semi-empirical models which rely on experimental data and assume a constant form vector across speeds can introduce systematic errors. As shown in the figure, Model 1 and Model 2 fail to accurately predict the peak of the resistance curve for FTS5. their exclusion of web and environmental effects further limits their reliability for real-world resistance estimation. In addition, according to Liu and Papanicolaou 2020, semi-empirical model under-predicted resistance by up to 26.2% in ballast and 76.4% in stern wave cases with low correlation values indicating weak accuracy. Limited data and challenging conditions, especially in beam and following seas, reduce the model's reliability, highlighting the need for refinement and further testing.
So next, I will continue the third problem statement. So this problem is aimed to design the optimum road to minimize the operational cost, travel time, and emission. So while adhering to practices, the constraints such as fuel capacities and port scheduling. So the findings demonstrate that road optimization can achieve a reduction of more than 7% of average in fuel consumption, travel distance, and journey time. So will it be, can road optimization really achieve this goal?
Yes, in my opinion, I think yes, route optimization can achieve this goal. So according to Address Breivik Omec ETAL 2003, the journal research state that using a high fidelity speed optimization models show even more potential. By factoring in real-time metadata such as wave height, direction, and periods. On fixed routes, the model significantly boosts efficiency with the result showing an average fuel reduction of 4.5% and up to 15% under harsher weather conditions. This supports the idea that combining smart routes and speed optimizations lead to real measurable reduction in fuel use, emission, and also travel times. Besides, according to Moradi EAL 2022, advanced methods such as reinforcement learning are also providing effectively. Techniques such as deep queue networks, PPO, and especially DDPG has been used to optimize ship routings. Among them, DDPG stood out, achieving fuel saving of 6.64% without time limits and 2.29% even with strict time constraints. This highlights that how AI-driven routings can further reduce emission, fuel use, and journey times.
Next, for the fourth problem statement is innovative optimization algorithms often not subject to incorporate this weather inference and constraint. So making it difficult to ensure that the final result is globally optimized. So making it difficult to ensure that the final result is globally optimized, is it still?
In my opinion, not necessary. So according to Wang at ETAL 2022, the recent advancement has addressed this issue. For instance, an improved and colony optimization model use continuous dynamic optimum control to incorporate real-time wind and wave data. It simplifies multi-stages decision into a single step and continuously update routes based on the changing weather. With a dual objective function that balance fuel consumption and sailing time, this model overcomes the limitation of statistic approach and deliver reliable, near optimal solution, even in complex maritime conditions. Besides, according to Zhao ETAL 2021, an improved particle swarm optimization, the genetic algorithm has been developed to specifically evaluate meteorological risks. It integrates the dynamic weather factors such as wind speed, wave height, and sea-keeping condition directly into optimization process. By combining the fast convergence of PSO with GM crossover, mutation and elite selection strategy, and enhancing the distribution of the Pareto fronts, this algorithm is capable of generating resilience and nearly globally optimal solution, even under complex and changing weather conditions.
In terms of recommendation, integrating weather routing and machine learning algorithms into travel planning is highly effective for reducing emission, travel time, and fuel consumption. The study by Ma et al. Introduced the rapid Gauss studio spectrometer, which is RGPM, which considers the kinematic characteristic of unmanned surface vehicle, which is USV, and addresses optimal path planning in complex maritime scenario. This method discretizes the continuous time path planning problem into a non-linear programming, which is NLP problem, and use iterative techniques to determine safe and nearly time optimal routes. Additionally, persistent modeling is crucial for improving navigational precision under dynamic conditions. Destogen et al. Developed a forward dynamic model tailored for supply vessel, incorporating physical and hydrodynamic parameters such as mass, rock, and maneuvering characteristics. This model accurately simulates ship behavior under different current direction, head, wind, and following, and support more adaptive ship-specific path planning, especially in challenging conditions like ballast or lateral wave impact. Looking ahead, the future of route optimization lies in the wider adoption of AI and real-time data integration. The development of RGPM reflects a broader industry trend towards reinforcement learning and AI-based planning, which are becoming standard tools for improving operational efficiency. This method also supports compliance with emerging carbon regulation, even if not explicitly tied to metrics like carbon intensity indicator, which is CII. The use of real-time environmental data, such as ocean currents, point to the creation of digital maritime corridors that allow constant update on weather, traffic, and routing. On the modeling side, the forward dynamic model by Testogen et al. Set the stage for digital twin system. These systems simulate realistic whole water interaction using accurate physical and hydrodynamic data, enabling high fidelity prediction of vessel resistance and motion in practical conditions. In conclusion, the integration of meteorological information routing and energy optimization offers a transformative path towards sustainable and efficient maritime transport. Through the use of real-time data, predictive analytics, and intelligence voyage planning, shipping company and can significantly reduce greenhouse gases emissions, fuel consumption, and operational costs while maintaining safety and delivery reliability. Although they are technological, financial, and regulatory challenges to address innovations such as AI-powered routing, digital twins, and advanced resistance modeling provide strong potential for overcoming these barriers. This integrated approach not only supports compliance with current regulation like IMO's SEEMP and CII, but also establish a foundation for future advancement in autonomous and environmentally responsible maritime navigation.